All right, so thanks for joining me, CS207. It is March 27th, 2020, and today we're going to continue talking about memory. Now I know that in the labs, you're doing EEPROM stuff. Is that right? You can vote yes or no in the participants window to give me feedback there. You're doing EEPROM stuff now? I mean, no is also an option. Okay, there is no lab yet. Oh, okay. Thank you. Yeah, they're okay. I think you're going to be doing in the lab. The next thing you're going to be doing is the EEPROM stuff. But there's no lab yet. Oof, okay. That's tough. It's really tough trying to adapt to this. And I believe that we're going to be running 207 during the summer, and so we got to figure that out. We got to figure that out real quick here. Anyhow, so let's just go on and keep talking about this. So where we last left off, I'm just gonna grab my notes from earlier. I was talking about the idea about memory, the idea of memory, and we did a little bit of a history lesson there, all the way up to electronic computer storage. Started talking about Arduino memory devices, and we're going to continue talking about Arduino memory devices today. I'm going to go back through the pools of memory, but we're going to talk about them in a bit more depth today. So, anybody remember what the, well, first of all, do you remember how many pools of memory your Arduino has? 3. Okay, what are those pools of memory?
Flash memory.
Yep.
SROM, RAM.
SRAM, yep.
EEPROM.
And EEPROM, exactly. And thank you very much for contributing. I do really appreciate it. Okay, yeah. So you have flash memory, you have SRAM, you have EEPROM. So we're going to discuss those 3 different types of memory today. But first, before we do that, I want to talk about the way that memory is generally arranged. And so to talk about that, I'm going to quickly share my screen here, and we're going to have a look at a couple of diagrams. So I'm going to minimize this, and here we go. Boop. And share. I'm going to share this part of my desktop. Okay, so you can see here, this is one of the ways that you can arrange memory. So you have one pool of memory, and you have a CPU that interacts with that memory. Okay, this is known as the von Neumann architecture. So you have the same memory for program variables and storage. And we've talked about the von Neumann architecture a little bit, but this is the memory unit of the von Neumann architecture. It is one unit that interacts directly with the CPU. Of course, the CPU will then interact with inputs and give outputs. So that is the von Neumann architecture. Now, there are, once again, what typifies the von Neumann architecture is that there's the same memory for program variables and for storage. Now, the other type of memory, generally speaking, is this. This is the Harvard architecture. And the Harvard architecture separates the data memory and the program memory into 2 different pools of memory. So you have data memory, program memory. Now, the data memory is, of course, accessed during runtime. It's where you store your variables. And we'll talk a bit more about that when we talk about our SRAM. And the program memory is, of course, where you store the programs. It's where you store the actual program, the actual sketch in the instance of the Arduino. Now, there are some pros and cons to each approach. So, of course, the von Neumann architecture here is much simpler. It's much simpler, and it's much more adaptable. So it's simpler, it's more adaptable. However, the Harvard architecture here is slightly better in performance because you're separating the program memory from the data memory. So when the CPU has to access the different parts of data, unlike with the von Neumann architecture where everything is all contained in one box, you don't have to basically search through that box. right? You know where the data memory is stored, so you don't even look in the box that also contains the program memory. That's a gross oversimplification of it, but I think that's a good analogy. So most computers you deal with today are actually hybrids. They have part von Neumann and part Harvard architecture built into them. So like your Mac and your Windows, your Linux boxes, most personal computers are a combination of these two. So you'll have different components operating with different types of memory. Now microcontrollers, however, must be at the peak performance, right? They must be at their best at all times. They don't have time to sort through and try to figure out what part of the memory pool is data memory and what part of the memory pool is program memory, because they are so constrained, and oftentimes they are inside of critical applications. Critical applications is a computer engineering term that means, like, for example, a life support system, things that need to be safe, and their failure could result in loss of life or loss of economic, loss of property. So, given this, because microcontrollers must be robust and must perform at their best capacity, what do you suppose is the best architecture for microcontrollers? Any guesses? Harvard, yeah, very good. Exactly. So microcontrollers generally use the Harvard architecture, because the Harvard architecture is much more, it performs better. So the Harvard architecture. So this is actually what the Arduino does use. The Arduino and a lot of microcontrollers are a pure Harvard architecture. So there's not a lot of mixing between the two architectures, right? Now, the way that I presented to you the model of interactive hardware throughout the semester was a more von Neumann looking diagram, but the distinction is at the level of memory, how the memory is handled. So that's something that's good to know, especially if you're a computer science major. It's good to know that the difference between the Harvard architecture and the von Neumann architecture really lies in how the memory is separated out. Okay, so that's the Arduino is a pure Harvard architecture. Now, programs are stored in Flash, as you already know. Programs are stored in Flash, and the variables are stored in the SRAM. Okay. So, oops, that is not the right picture. I'm going to stop sharing the screen and go back to Zoom. I got to figure out, there must be some keyboard shortcuts that I can use for this. Okay, so like I said, you have programs that are stored in flash memory, and you have variables stored in the SRAM. Now, flash memory, let's go and talk about flash memory for a moment. So once again, flash memory is where the program is stored. And so unlike the SRAM, you cannot modify the flash memory during runtime. Okay, this is inaccessible during runtime because it's where the program is stored. Okay, the program is stored inside of the flash memory, so you don't manipulate it during runtime. So the flash memory is the same kind of memory that you find in things like thumb drives, or in like one of these guys. Any idea what this is? Just gonna see if somebody's commenting in the chat. Any ideas, any guesses what this is? A memory card. Yeah, well, it is a memory card, but it's a special type of memory card. Here, I'll give you another clue. If you look on the back, I think you should be able to see that. Do you see that? The logo there? Yeah, it's a game cartridge. This is a Nintendo DS, a Nintendo DS game cartridge. It's just it happens to be naked. anyhow, so you see on here that you have right here, this little chip here. This chip there is a, let's see here, S104808. So I'm not quite sure exactly. I haven't looked at this, but this chip right here is a ROM flash cartridge. Okay, so it's a ROM flash cartridge. This guy right here. So this is the same thing that is in that this is the same type of memory that is in your 18 mega. But also, if you take a bunch of these and you string them together, you get one of these. Anybody know what this is? Boop, boop, boop. So I'll let you cheat and I'll show you the label. Solid state drive. Yeah, it's a solid state drive. Now, actually, I'm going to pop this open and you can see. So the inside of the solid state drive, you see there, that is a solid state drive on the inside. It's just a whole bunch of little thumb drives that are all kind of stuck together. You can see the same thing going on here, right? So it's really the same technology. They just stuck a bunch of them. Oops, I just dropped that. They just stuck a bunch of them together. So flash memory. It's the same kind of technology that you find in SD cards, same kind of technology that you find in thumb drives. It's the same kind of technology. But now the reason why we call it solid state, the reason why we call it solid state is because there's no moving parts, right? Obviously, there's no moving parts in this hard drive. It's all just on the chips. Just gonna put this back together properly because this has important documents on it, and I probably shouldn't be taking it apart, but whatever. It wouldn't be mine if I didn't take it apart, right? You know what, I'm just gonna set this over here. So unlike something like, say, one of these guys, right? This is a standard hard drive, and you can actually hear if I shake it. I shouldn't shake these, but you can hear there the moving parts rattling around on the inside. So unlike those guys, solid state drives, so like thumb drives and flash memory, SD cards, they don't have any moving parts. Okay, so this makes them much quicker than, say, our rotating disk. A rotating disk in these guys makes them much quicker. It also makes them less likely to have technical faults, so less likely to fail, because you don't have a little arm that has to reach out and actually read and write. Has any of you taken apart a hard disk before? I wouldn't recommend opening one up unless, of course, you want to really mess it up. I'm just going to open up an image here just to show you what it looks like on the inside. Let's see here. So this is a Shutterstock. Actually, it's a video. So I'll try to share my screen here because I think that you should see this because it's pretty cool. Okay. There you go. All right. So you can see here, this is what it's like. This is what's inside of one of these little guys, right? So you got your platter, and your platter is spinning around in circles really fast. And then you have the arm, and the arm comes out, and like I said before, the arm rotates little, basically electromagnetic filings that are scattered around the platter. And as it rotates when it rotates those, one orientation means a 1, one orientation means a 0. So this is how, let's just run that one more time. This is how a standard hard drive operates. So that's pretty cool. It's pretty cool. It's pretty cool that with the solid state drive, you don't have these moving parts, so it's less likely to fail. More often than not, when a hard drive fails, if it's not a solid state hard drive, more often than not, when it fails, it's going to wind up failing on that little lever arm. As you can imagine, anytime you have moving parts, you always have a likely chance of failure. Okay, so going back, they're known as solid state. Well, first of all, because they don't have many moving parts. It's more sophisticated than that. I'm not going to get into it, but it also has to do with solid state physics. But so flash memories are non-volatile. Okay, and flash memory has only about 100,000 read-write cycles. So you could upload 10 programs a day for 27 years before it wound up not being able to read and write to it anymore. See where we're going with this. Okay. So another cool thing about the way that flash memory works is that these chips, so here's, once again, your ROM cartridge. Contained within those chips, the way that it works is contained within those chips is literally just a buttload of transistors. So a bunch of little transistors, and they're all wired together inside of these little guys. So there's millions and millions of transistors all wired together. And so what happens when you are reading or writing to a solid state disk, what happens is that you send a little electrical signal, right? Send a little electrical signal to the little transistors that live inside here, and you tell them, turn on or turn off, and they will stay on or off until they're told to change otherwise. So they're a special type of transistor called MOSFET, and I'm not going to get into MOSFET transistors with you guys, but just know that inside of this little guy is hundreds and millions of little transistors. That's how solid state memory works, and that's kind of why it's a little expensive still. It's because it's rather complicated configuration. Okay, so the next pool of memory that we're going to talk about is the static random access memory, so SRAM. Okay. Now, the SRAM is where the variables get stored during runtime. So this is the pool of memory that during runtime we access. Okay. Now, it has three main components, and I'll show you a little picture here of what those three main components look like. Excuse all my clicking. Okay, so you've got three main components. So first at the bottom here, this is the static data. Okay, so this is where all the global variables and constants live. And that's why they're called static. It's because you have this area that is only read to and written from, other way around, that is only written to at the very beginning when you're compiling everything. So this is the static data, and it's static because it does not change at all. Okay. Well, at least during runtime. Now, the next piece here is called the heap. Now, the heap is a dynamically allocated pool of data, and that dynamically allocated pool of data will grow from the bottom, upwards. That is the heap. Now, the heap grows from the top of the static area, and it expands upwards into this free memory space. Sorry. Now, on top of our bunch of memory here, you have the stack. Now, the stack is where the local variables get stored. So this is for your local variables that you manipulate during runtime. And the stack also grows, and it grows from the top downward. Okay. So the stack and the heap, they actually have to compete for kind of the same free memory resources. And now this is where you can wind up with a bit of a problem. So if you try to allocate too much data, what can happen is this. So you have a normal SRAM operating, and what can usually happen is the heap grows uncontrollably and winds up slamming up against the stack, and that's called a stack crash. because the heap slams up against the stack. Now, what happens a lot of the time is you wind up with fragmentation. Now, fragmentation is a fancy word, basically saying that we're not using the memory intelligently. So illustrated here, you can see all these little purple circles. So those are meant to stand for parts that are being used or not being used, sorry, parts that are not being used properly. So they're usually like basically little holes of garbage data, right? Little holes of garbage data that didn't get cleared properly or aren't being written to properly. And those tend to add up. And so the rest of the information winds up eating up the memory, and then you wind up slamming up against the stack. And so you wind up with a stack crash. So we don't want to do this. This is more often than not, if you aren't having a problem with having a program that is too large for the flash memory, this will be your other problem, is when your heap and your stack collide. Okay. Now, the last pool of data that we haven't talked about yet is the EEPROM. Now, the EEPROM, you are hopefully going to be doing a activity in lab where you interact directly with the EEPROM. Now, the EEPROM is another pool of volatile or of non-volatile memory. Okay, so you've got two pools of non-volatile memory. Okay, the first pool is, of course, the flash memory, and that's where the programs are stored. And the EEPROM is the second non-volatile pool of memory. And this non-volatile pool of memory, unlike the flash memory, can be written to and can be read from during runtime. Now, this is kind of useful, and I'll talk about it in a bit. But one of the problems with the EEPROM is, first of all, it can only be written to or read from 1 byte at a time. So if you want to access a certain area of the EEPROM, you have to literally read every single byte in the entire array of bytes in order to get to that piece of information. And you'll do this in lab, but let's say that there are 255 sectors that in the EEPROM that you can store information from, and you can only store integers. By the way, that's another thing that's interesting. You can only store integers. So you'll store an integer from 0. I think you can store an integer from 0 to 255. I'm getting this confused. Integers from 0 to 255. How many integers can you store? That's a good question. Let's see here. Just gonna have to look that up because I have now forgotten that. Arduino EEPROM. Let's have a look here. EEPROM. You can, let's see, how many spaces does it have? EEPROM get, nope. How many spaces does Arduino EEPROM have? I know you can't see this. Okay, so it has 1,024 spaces. Okay, so it's got 1,024 spaces, and you can store a value between 0 and 255 for each space. Now, thing is that if you want to get to, say, I don't know, if you want to read the value at space 1,000, right? You have to read every single value along the way. So you have to read all 999 values before you get to the value that you want. Okay. So that is obviously a drawback. That will be much slower than, say, your flash memory or your SRAM. Another problem with the EEPROM is that it only gives you 100,000 write cycles. Okay, so you can only write to it 100,000 times. You can read to it as many times as you want, but you can only write to it 100,000 times. And then it's kaput. So it is something that you have to be careful with. Now, I think I told you about this before, that when I was first starting out working with eSolables, I had sewed myself a watch, like a little a wristwatch, right? And it used an Arduino LilyPad. I told you this already, but I'll just remind you. So the Arduino LilyPad, e-sewables, the thing about e-sewables is that they are flexible, right? Because they have flexible thread, conductive thread that serves as the wire. So one problem with it is that whenever I would move my wrist like this, there would be a short circuit and it would cause the Arduino LilyPad to brown out. I don't know if you remember what the Arduino LilyPad looks like. Arduino LilyPad watch. Let's see if I can find you. I had something that looked kind of like this, actually. Oh, sorry, got too much stuff on my desk. So here we go. This is pretty much exactly what it looked like. Gonna share my screen. All right, so yeah, this is pretty much exactly what it looked like. My Arduino LilyPad watch, except for it didn't have this guy here. But anyhow, so this is what the LilyPad watch looked like. And so you can see here, it's not, oh, bit image in your tab. Okay, boop, there you go. So you can see here, this is how an Arduino LilyPad works. So you have this conductive thread, right? And that's sewed into each of the little holes. Now the cool thing about this is, of course, you can sew it into fabric. And so I had this idea, I took a pair of ripped jeans and I cut them out and I made a little wristwatch out of it. And so the idea was that like you have, I had 12 lights, and as the time progressed, of course, you would light up, say it was like, I don't know, 12:30, you'd have this light lit up, and then you'd have this light at the bottom lit up, right, to denote 12:30. Now the problem is, of course, because it's floppy, it would short circuit whenever I would bend my wrist the wrong way. So I had this brilliant idea, and the brilliant idea was to write the value of the time, right, the time to the EEPROM every second, right? So you could probably like guess why this was a bad idea. Why was this a bad idea? Y'all can feel free to unmute yourselves. Why is this a bad idea?
Since you,
oh, go ahead.
Since you can only write to the EEPROM so many times, you burnt through that really quickly.
Exactly. So you can only write to it 100,000 times. Now, hey Google, how many seconds are there in a day? Take your time, Google. 1,000, that's how many days in a year? Hey Google, how many seconds are in a day?
1 day is equal to 86,400 seconds.
86,000, right? So you're already almost out of writes by the end of 1 day. Yeah. So I was a dum-dum and I thought, hey, I would write down the time every single second. And yeah, needless to say, that didn't last very long. Because every time you'd short circuit it, it would reset the time and yada yada. Anyhow, but this can come in handy, and this is exactly the kind of scenario that it might come in handy for, because the EEPROM is a non-volatile memory that you can write to and read from during runtime. You can use it in order to store the state of a device in case of a shutdown, in case of a short circuit, or in case you unplug the thing. Now, of course, you want to be very careful with how many times you write to it, but it's really kind of cool. It's a cool thing that you can do. It's useful to keep track of previous states, even if the system shuts down. Okay. Now, given that we have all of these different, given that we have all of these limitations. It's very important that you are careful with how you optimize the use of your memory. So when you compile a sketch, the IDE will tell you how big the program image is, right? So you know what I'm talking about. When you compile the sketch, it'll tell you exactly how big. You know what, I'll show you. I'll show you. Just give it a sec. Or 2. Or 12. Okay, here we go. So I'm going to go ahead and share this over here. Boop. Share. All right. So let's go ahead and I'm gonna import a, let's see, sketchbook. Let's go examples, basics. Screw it. I'm just gonna grab a digital blink without delay. Whatever. Here we go. So here's that. Here's that spec. Can you see the blink without delay? Or did it stick with the other one? Can you guys see the blink without delay? No, okay. Thank you. That's all I needed. Okay, I'm just gonna, then I'll stop the, change the screen share, new share. Let's go and let's change this to blink without delay. There you go. Cool. Now you can see that, right?
Yes.
Thank you. Okay, cool. So if I compile this, okay, you see here, right down here, binary sketch size, 1030 bytes of 32,256 byte maximum. Okay, so right here, it will tell you exactly how much of the sketch that you, how much of the memory that you are using with that sketch. Okay, so you want to be careful with that, right? Because there is only 32,000 whatever maximum. So when you compile your sketch, it'll tell you how big the image is. And if you've reached or exceeded the space available, some optimizations that I'm going to talk about here might help you get back under that limit. So this is not meant to be like, I'm not going to tell you how to optimize your code like in any definitive way, but here's some easy ways of doing it. So the first thing you can do, is remove dead code. Okay, if you're above the flash memory, you can remove some dead code. And what I mean by that is sometimes you might be importing libraries that you're not actually using. I do this all the time. Like I'll import a library and I'll think that I need it, and then later on I won't use it. But it's still you've got, if you're going to call a library, you've got to compile it onto your Arduino. So are all the include libraries, are they actually used? So first thing. So make sure that you check that. So the second thing, are you calling all of the functions? So look and make sure that every single function call that you have in your program, that there aren't any dead ends, right? And a dead end, what I mean by that is that you don't have like a function that's never called inside of the main program. So check to make sure that you are being careful with your unused functions. Also, are you declaring any unused variables? If you're declaring any variables and you don't use them, then you're going to wind up using a lot of space that you don't need. And then also make sure that you don't have any, like, check to see if there is any unusable or unreachable code. And so this is whether or not there are conditional expressions that can never be true. So for example, if you have an if statement or something that can never be true, what's the point of having the if statement, right? So those are some things that you can look into. So a way of doing this, of testing to make sure, is to comment out. So for example, if you have an include, comment it out. And if the file, going back to libraries, sorry, if you have an include, if you're including a library, one way to check to see whether or not it actually is used is to comment it out. If the program still compiles, that means that the library is not being used. And libraries can take up a lot of room. So that's one place that you can really save yourself a lot of room. Another thing that you can do is consolidate repeated code. So if you have a same sequence of code segments, if you're using a lot of, if you got a series of if statements, just a whole bunch of them, maybe look into using a while loop, something like that. So consolidate repeated code. If you use the same code over and over and over again, and you have a bunch of, say, if statements that could be squished down into a smaller statement, you can do that. Also, space is really, really, really tight. Okay, and this is only like a last ditch effort, and you should know what the hell you're doing here. If it's really tight, you might consider getting rid of the bootloader. So I think I mentioned this already, but the flash memory, while we don't have a operating system, we do have a bootloader, and the bootloader is there just to basically, when you start up the Arduino, to tell it how to get things moving, right? You can delete the bootloader, and this can save like 2 kilobytes to 4 kilobytes of flash memory, depending upon what bootloader is loaded onto it. Now, the downside of this is that you're going to need to use an ISP programmer instead of the standard USB cable. So I talked about ISP. I talked about the IIC interface. You're going to have to hardwire into it in order to program it. So that is a downside. Okay. Questions about any of that so far? I know I've been kind of going kind of fast. Could slow it down a little bit. It's hard when I can't see your faces. I just think I have to fill every last second with a whole lot of jibber jabber. So let me know if you got any questions at all. Nope, no questions, no questions. Okay. All right. Cool. Okay. So just gonna scoot this up here so I can see that. Good. Now, when it comes to SRAM, okay, so when it comes to the SRAM, this is the most precious commodity, the most precious memory commodity that the Arduino has. Okay. SRAM shortages are probably the most common memory problems on the Arduino. So you wind up running out of space. And they also are the hardest ones to diagnose. So if your program is failing, right? If your program's failing and you can't figure out why the hell it's failing, it doesn't make any sense. This might be an SRAM problem. Okay. So if your program's failing in an otherwise inexplicable fashion, chances are that you have caused a stack crash. So there's a number of things that you can do to fix this, so to reduce the amount of SRAM that you use. And these, I'll give you a couple of pointers here as to what you can do. So first of all, remove any unused variables. So if you don't use a variable, don't initialize it. There's no point in initialize it. Okay. Another thing that can really, really kill it really fast are strings. Okay. So how many of you are using, like, say that you're printing out to serial, how many of you are using strings in your program for your project? Like, are you writing out maybe for debugging or something? Nope, I don't see anybody. Okay. So none of you are using serial.println. No? Okay. I'm surprised at that. But anyhow, strings are memory hogs. Strings are massive, massive memory hogs. And they're a horrible waste of SRAM. So try to avoid using strings. If you don't need them, don't use them. And reserve those strings for when you really, really need them. Okay. Just looking through my notes to see if there's anything else that I need to cover quickly. Okay. So some of this you're going to talk about in lab. So in your lab, I think probably next week, you're going to talk about reading and writing to the EEPROM, and you're also going to talk about progmem. Okay, I'm not going to talk about progmem today, but you're going to talk about using progmem. You know what? I'll talk a little bit about it. So data items, you can declare data items as progmem Progmems is of course short for program memory, and these are bits that do not get copied into SRAM at the startup. So progmem, you'll talk about it. I'm not going to go into a whole lot of detail because it's easier to do one-on-one. Okay, so that is pretty much all that I wanted to talk about when it comes to the Arduino's memory itself. I think the next lecture I will talk about using external memory. So how to like add stuff, like you can add SD cards, or you can do stuff like add an external ROM chip to your build. But I think I'm gonna leave the Arduino for now. So we're gonna move on from that. And so the next lecture, Monday's lecture, we will talk about how you can write to an external memory source. Okay, any questions? No? Okay, so I'm gonna stop the recording. And I'm gonna stick around for a little bit until everybody's left. And if you have any questions afterwards that you wanna ask me, please feel free. So I'm gonna stop the recording now.